Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Fairbaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, in this lesson, we're going to continue our discussion of Unit 4, Chemical Reactions. I just want to remind everyone that you can always go to the College Board website. In this case, the address is apstudents.org/exams2020. to get more information about the at-home online AP exams this year. So feel free to check out that resource. Make sure that you have access to paper and pencil and a periodic table. And let me give you an overview of today's lesson. So we're going to finish up Unit 4 on chemical reactions. So we'll talk about stoichiometry. We'll talk about titration, various types of chemical reactions, including acid-base reactions, oxidation-reduction or redox, and precipitation reactions. So as you can see here, also there are a variety of science concepts and skills, including balancing chemical equations and describing the components of quantitative information from models and particulate-level and macroscopic-level properties. So in today's lesson, we will talk about stoichiometry, titration, acid-base reactions, redox reactions, and precipitation reactions. Let's begin with the problem that I had set for homework from yesterday's lesson. And it involved a laboratory experiment in which a tablet containing potassium iodide, Ki, was analyzed to determine the iodide content. And so the tablet was dissolved in distilled water, and an excess of 0.2 molar lead nitrate was added. A yellow precipitate forms, which was then filtered, washed, and dried. So we have this data. And then we have parts A through F. So we'll go ahead and start with part A. For the chemical reaction that occurs when the precipitate forms, write a balanced net ionic equation for the reaction and explain why the reaction is best represented by a net ionic equation. So as you recall from yesterday's lesson, if you have a soluble ionic compound, we're going to split that up into ions. So each of these chemicals, the potassium iodide and the lead nitrate, are soluble in water. It's going to be a reverse, kind of a double replacement reaction where you switch partners. So now the potassium bonds with the nitrate. So we have potassium nitrate and then the lead iodide. So I said in yesterday's lesson, as I balanced this equation with putting a 2 in front of the Ki and a 2 in front of the KNO3, in yesterday's lesson, I said that all sodium, potassium, ammonium, and nitrate salts are soluble in water. So that means that potassium iodide, lead nitrate, and potassium nitrate are soluble, and our precipitate happens to be the lead iodide. So if we're going to write a balanced net ionic equation, let's go ahead and convert this molecular equation into the complete ionic equation where we split up everything that we can. So I have 2 potassium ions and 2 iodide ions. I have 1 lead ion, which is +2, and 2 nitrate ions. And then on the product side of the equation, I have 2 potassium ions and 2 nitrate ions. And because lead iodide is our insoluble or slightly soluble ionic compound, we'll go ahead and leave that formula together. And once I cross off the potassium and the nitrate as our spectator ions, this now becomes our net ionic equation. So that takes care of part A, Roman numeral 1. In Roman numeral 2 of part A, explain why the reaction is best represented by a net ionic equation. So you might wonder, why exactly do we cross off the spectator ions? Well, it's because they're not changing in this particular reaction. They are the same on both sides of the equation. So the net ionic equation shows the formation of the solid lead iodide from the aqueous lead and iodide ions, and the spectator ions are eliminated from the equation because they are unchanged by this reaction. In part B, explain the purpose of drying and weighing the filter paper with the precipitate 3 times. Well, as you might imagine, it says a yellow precipitate is filtered, washed, and dried. That is a solid. So the precipitate being a solid, it should be as dry as possible. We don't want to put lead iodide that is wet with water on the scale because it would not give us an accurate mass of just the solid itself. So the filter paper and the precipitate must be dried several times to make sure that all the water has been removed. And as you can see, between the second and the third drying, the procedure is repeated until eventually the mass remains essentially constant. All right, well, that takes care of part B. Part C is a little confusing at first. In the filtrate solution, is the concentration of potassium greater than, less than, or equal to the concentration of nitrate? So you might wonder, what exactly is the filtrate and what does this procedure look like? There wasn't an actual setup or an experimental diagram other than a table. So let's go ahead and talk about what actually happened. So this is a tablet, and this tablet contains potassium iodide as well as an inert water-soluble sugar as a filler. So we're going to take this tablet and dissolve it in 50.0 milliliters of distilled water. So to give you an idea of what that looks like now, sort of a particle diagram, we now have a solution that contains some sugar, which is not going to react in this case, and then some potassium ions and some iodide ions. Now remember that the iodide is part of the net ionic equation. The potassium is a spectator ion that will just remain in solution. So now we add this excess amount of lead nitrate. And so in our particle diagram, you can see that we still have the sugar and the potassium and the iodide, but here come lead ions and nitrate ions. Now, this is sort of frozen in time because the moment that that lead nitrate hits the solution, there would be an immediate formation of this solid yellow precipitate, which I'm showing on the bottom of the beaker here. So consider we have some potassium ions that still remain, but all of the iodide ions are now sitting in the bottom of the beaker and the form of solid lead iodide. So the question was asking essentially about the filtrate. So if we take this solution and we pass it through a filter, then we can collect the solid lead iodide in the funnel and the filter paper, but we have filtrate, which is what passes through. That's all the soluble ions. So as you can imagine, potassium ions and nitrate ions are not going to have the same concentration. So the key word there in the stem of the question is the word excess. So because the source of the nitrate ions in the solution is excess lead nitrate, then the nitrate concentration should be much greater than the concentration of the K+. So the official answer to this question is the concentration of K+ is less than that of nitrate. All right, now time to look at your periodic table, because in part D, we have to calculate the number of moles of the precipitate that is produced in this experiment. So on your periodic table, you can find the formula for lead, which is Pb, and it has a molar mass of 207.2. And on the periodic table, the molar mass of iodine is 126.9, and we have two of them in the formula of the precipitate, which is lead iodide. PbI2 has a molar mass of 461.0 grams per mole. We can subtract the mass of the filter paper from the final mass of the filter paper and the precipitate after it was dried several times. So that difference is 0.236 grams of lead iodide. Let's convert that from grams to moles. And now we have 5.12 times 10 to the minus 4 moles of lead iodide. That is our answer to part D. Part E asks us to calculate the mass percent of iodide in the tablet. So since the mass of iodide comes from the lead iodide, which we already know the moles of, let's convert moles of lead iodide into grams of iodide. Now remember, there are 2 moles of iodide for every 1 mole of PbI2. Again, the periodic table tells us that there's 126.9 grams of iodine for every 1 mole. And it doesn't matter whether it's I, the atom, or I minus, the iodide ion. That's not going to change the mass. A single electron is not going to make a difference. So if we do this math, we get 0.130 grams of iodide. So the percentage of iodide in the tablet is going to be a mass ratio. 0.0130 grams of iodide divided by the mass of the tablet times 100, and that gives us approximately 30.6% iodide by mass. All right, the next part of this question said, if we had used, instead of 50.0 milliliters of distilled water, if we had used 55.0 milliliters of distilled water to dissolve the tablet, is that going to affect the mass percent of iodide? And if so, is it going to be greater than, less than, or equal to the amount that we just calculated in part E? We'll go back to that procedure. Dissolving the tablet in a larger volume of water, we're still going to add the excess lead iodide to react. The lead nitrate to react with all of the iodide. We're still going to take that precipitate and filter it. So effectively, whether that is a larger volume of water to dissolve the tablet, it's not going to make a difference. We're still going to dry the precipitate. So the mass percent of iodide should remain the same because lead was added in excess, ensuring that all of the iodide reacted. Any additional water is going to be removed by filtration and drying, and the mass of that dry precipitate should be the same. All right, let's go on to our lesson. We're going to start with stoichiometry. And with respect to stoichiometry, I'd like to talk about conversions of moles to moles, grams to grams. I'd like to connect stoichiometry to molarity, the ideal gas law, as well as talk about limiting reactant and theoretical yield. So I'm going to come up with an unbalanced chemical equation that will deal with all of these concepts. Here we have a reaction between aluminum or aluminium and a solution of hydrochloric acid. It produces a solution of aluminum chloride and hydrogen gas. This equation is not balanced. I see two hydrogens on the right, so I might put a 2 here to balance the hydrogens. But upon closer examination of the chlorine, I realize that I have 2 chlorines on the left and 3 chlorines on the right. So the least common multiple of 2 and 3 is going to be 6. So I'm going to have to get 6 chlorines on both sides. Now that I have 2 aluminums on the right, let's go ahead and balance the aluminums. And then finally, 6 hydrogens. There's a 3 right there for 6 hydrogens. So we're going to do moles to moles. Moles to moles involves the coefficients, and the ratios 2, 6, 2, and 3 represent the relative number of moles of each substance. Here's an example of a moles to moles question. Aluminum or aluminium and hydrochloric acid react together according to the chemical equation shown above. If 0.36 moles of aluminium chloride is produced in this reaction, how many moles of hydrogen are also produced? So what you would do to convert from moles to moles is you would put the units you want to get rid of on the bottom. So in this case, moles of aluminum chloride on the bottom. And then we want moles of the other chemical, which in this case happens to be hydrogen, on the top. We don't need the periodic table to do moles to moles. We just need the coefficients. So the coefficients from the balanced chemical equation are what I would use to convert moles to moles. So you can go ahead and do this math and see if you get the same answer that I do. Feel free to pause the video at any time during this lesson to stop, check your work, and then you can press play to make sure that your answer is consistent with the answer that I'm giving you in the lesson. So hopefully, if you did this math already, you would have gotten 0.54 moles of hydrogen. Now let's move on to a grams to grams conversion. So same reaction, but now aluminium and hydrochloric acid react. How many grams of aluminium are required to produce 75 grams of hydrogen? You can assume that the hydrochloric acid is added in excess. So we have 75 grams of hydrogen, and we're going to try to figure out how many grams of aluminum or aluminium are going to be required for 75 grams of hydrogen to be produced. This first step will be what I call a periodic table step. This second step will involve the coefficients, as I was just showing you in the example from moles to moles. And then this last step will also be what I call a periodic table step. So here, we're going to involve the periodic table. And approximately the number of grams of aluminum in 1 mole, about 27 grams according to the periodic table. This is also a periodic table step. Approximately, for every 1 mole of hydrogen, that is about 2 grams. So I got that information off the periodic table, but this comes from the coefficients. So I would put moles of hydrogen on the bottom, and I would put moles of aluminum on the top, and I would use the coefficients, in this case, 2 and 3. So that is the setup for this problem. Again, you can take the time to do that setup on your own. You can use the periodic table and the coefficients, and you can pause the video and see if your answer agrees with mine. So here are the 3 steps: grams to moles, moles of hydrogen to moles of aluminium, and then finally moles to grams. So when I did this on my calculator, I got 670 grams of aluminum or aluminium. All right, moving on to a next example, I want to connect molarity. So molarity is moles per liter. This question says, how many milliliters of 5.0 molar hydrochloric acid are required to react completely with 4.25 grams of aluminum? So if I have 4.25 grams of aluminum, I have to somehow get to volume of hydrochloric acid. Remember that this capital M, so right here, this capital M, that means moles per liter. So there are 5.0 moles of hydrochloric acid for every 1 liter. I can use that as a conversion factor if I need to. Let's convert grams to moles using the periodic table. Let's convert from moles of aluminum to moles of hydrochloric acid using the coefficients. And then now we're not going to convert to grams like we did before. We're going to convert to volume. So I'm going to use that conversion factor, but it's going to be upside down. 5 moles of HCl on the bottom and 1 liter on top. If I stop right now and did the math, my answer would come out in units of liters. So I'm going to add milliliters, and you should know that there are 1,000 milliliters in 1 liter. All right, if you've done this math, you've done 4.25 divided by 26.98 times 6 divided by 2 divided by 5 times 1,000. Hopefully you got the same answer that I did. 94.5 milliliters of 5 molar hydrochloric acid is required to react completely with 4.25 grams of aluminum. I want to make a connection to the ideal gas law because, again, stoichiometry involves moles, and moles are connected to a variety of topics. So with respect to the ideal gas law, PV equals nRT, where P is pressure, V is volume, and N is number of moles. And then R is the ideal gas constant, which you can get off the formula as an equation sheet on the AP exam, and then T is the Kelvin temperature. So here is our problem. 35 grams of aluminum reacts with excess hydrochloric acid. What is the volume in liters of hydrogen gas produced at a temperature of 345 Kelvin and a pressure of 1.12 atmospheres? So if I'm looking at what is the volume of hydrogen gas at a certain temperature and pressure, I'm going to write V equals nRT over P. They've already given me the pressure in atmospheres, the temperature in Kelvin. I can use the ideal gas constant, that number that we'll see on the equation sheet, 0.08206, which has the appropriate units of liters and atmospheres. But what I have to figure out is the moles. So where's the moles going to come from? That is going to be the stoichiometry. I've got to connect 35 grams of aluminum into moles of hydrogen. So we'll start off this problem by converting 35 grams of aluminum into moles. That's just the periodic table. Let's convert from moles of aluminum into moles of hydrogen. But now I'm not going to go to grams. I'm going to take that number and plug that into the ideal gas law. So when I did this math, I got 1.95 moles of hydrogen, and that will be the N in my expression. V equals nRT over P. And looking at the units, the ideal gas constant has units of liters, atmospheres, moles, and Kelvin. Everything will get crossed off except for liters. So if you do this math, 1.95 times 0.08206 times 345 divided by 1.12, you should get your answer in units of liters. And I did this on my calculator, and I got 49 liters of hydrogen. All right, next thing I want to talk about in the category of stoichiometry is limiting reactant and theoretical yield. So we're given a problem involving two different reactants, aluminum and hydrochloric acid. 125 grams of aluminum reacts with 2.50 liters of 3.20 molar hydrochloric acid. Which chemical, the aluminum or the hydrochloric acid, is the limiting reactant, and what is the theoretical yield of hydrogen in units of grams? So there's two ways to solve this problem. I'm going to show you both ways. I'm going to start with this particular method. I'm going to convert each of these reactants into grams of hydrogen. And when I do that, then we can compare and see which mass of hydrogen is smaller. So let's start off by converting from grams of aluminum into moles. That's the periodic table. Let's convert from moles of aluminum to hydrogen using the coefficients. And now let's convert from hydrogen moles to grams, periodic table. So while this number, 14.0 grams of hydrogen, is not necessarily my final answer, it is a point of comparison. So I'll start the same process over again, but using the other reactant. Now I can't begin with grams of hydrochloric acid. I'll begin with the volume. Let's use 3.20 moles per liter as a conversion factor. Let's put moles on the top and liters on the bottom so they cancel out. Now, let's convert moles of HCl into moles of hydrogen using the coefficients. And then my final step back from moles to grams, and I get, okay, so I've got two numbers here, 14.0 and 8.06. So by definition, the limiting reactant limits how much you can produce. So therefore, the limiting reactant in this case will be HCl, because it produces a smaller amount of product when I do my stoichiometry calculations. Now, the theoretical yield is the maximum amount of hydrogen gas that I can produce from these two reactants. So the theoretical yield of hydrogen in this case is the smaller of the two values. So 8.06, that's my theoretical yield. Let me show you the other way to solve this problem, and it has to do with converting each reactant into the other reactant. As far as converting one reactant into the other, it's going to be the same principle of stoichiometry and mole ratios, but now I'm going to convert aluminum into hydrogen. I'm sorry, not hydrogen, hydrochloric acid. So I'm going to convert aluminum into the other reactant, so hydrochloric acid, and then I will go to volume by using the 3.2 moles per liter, that ratio upside down. So I have moles on the bottom and liters on top. If I do this math, I get 4.34 liters of the hydrochloric acid needed. Now let's compare the amount that we need with the amount that is available. Hopefully you can see that HCl is the limiting reactant because the amount you need to react with all of this aluminum is greater than what you have available. So you're going to run out of the hydrochloric acid. You don't have enough hydrochloric acid to react with all this aluminum, so therefore it is the hydrochloric acid that is going to be limiting and to be consumed completely. If we go the other way and start with the hydrochloric acid, convert that from liters to moles using molarity, convert to moles of aluminum using the coefficients, and then finally to grams with the periodic table, notice that the amount of aluminum that I need is less than in what I have available. So it is the aluminum that is present in an excess amount because I have more aluminum available than I need to completely react with the hydrochloric acid. Now I like both methods. They're both fine methods. I think I have a slight preference for the method that I showed you first. And the reason I like this method is because if the question follows up with the theoretical yield, then you already have those numbers right there. You've already done the work. If instead they ask you for the theoretical yield of hydrogen, you still have to convert all of the hydrochloric acid into hydrogen. So I feel like the first method kind of accomplishes both of those at the same time. It tells you the limiting reactant and it gives you simultaneously the theoretical yield. All right, moving on to the next topic in today's lesson, titration. Here we see a burette and a flask. So a titration is an experiment that can be used to calculate the amount of moles or the concentration of one chemical by reacting it with a known quantity of another chemical. The standard solution, that is the concentration that you know, is called the titrant, and the solution with the unknown is called the analyte. So in this case, for that little setup here, I've got the titrant in the burette, that's the one I know, and then the analyte in the flask, that's the one I don't know. It might be backwards. You might have a known amount of chemical in the flask, and you might fill the burette with an unknown solution. So it's still possible that the chemical that is unknown could be in the burette. I'm just going to go ahead and show you this particular example. So the titrant is slowly added to the analyte by using the burette, and then the equivalence point is reached. And the equivalence point in a titration is the point at which just enough titrant has been added. So based on whatever chemical reaction you're doing, it could be an acid-base reaction, it could be an oxidation-reduction or a redox reaction, even a precipitation reaction. There's a variety of reactions you could do. The equivalence point is when enough titrant has been added to react completely with all of the analyte. And this point may be indicated by a color change. And if that color change happens, then the observable event would be called the end point. And you want the end point to be as close to the equivalence point as possible. So we normally design our experiment so that the color change happens very close to the equivalence point. All right, so for titration, I'm going to give you an acid-base reaction to start. So the chemical on the left is called acetic acid, also known as ethanoic acid, and that's found in vinegar. So we have a solution of vinegar, and it contains an unknown amount of acetic acid, HC2H3O2. That is a monoprotic acid, has one H plus that is given off as an acid. A 25.0 milliliter sample of vinegar is titrated with 0.650 molar sodium hydroxide according to the equation above. If it requires 32.04 milliliters of the titrant to reach the equivalence point, what is the concentration of the acetic acid in the vinegar? So we'll convert milliliters to liters. And then because 0.650, that's the number of moles in 1 liter, we now have converted from liters to moles using molarity as a conversion factor. Notice that the equation above is balanced. Monoprotic acids require 1 mole of sodium hydroxide to reach the equivalence point and neutralize it. That's a 1-to-1 ratio. So right now, this is not my final answer, but that's how many moles of acetic acid I have. I'd like to figure out the concentration, which is moles divided by liters. So 25.0 milliliters, that would be 0.0250 liters. Oh, that should say liters. Sorry about that. That should say liters right here. So we're going to do our conversion factor to get concentration by doing moles divided by liters. And if we do this math, we get 0.833 moles per liter, or capital M. Now, there is another way to solve this problem. And the second way to solve this problem is a little easier. And I caution you to use this carefully. This is a shortcut. If there is a 1-to-1 mole ratio between the acid and the base, you can also use the following equation as a shortcut. So capital M is molarity, capital V is volume. So we have molarity times volume for the acid and molarity times volume for the base. Because molarity times volume is moles, the moles of acid equal the moles of base. So if you plug in everything we know from this problem, we don't know the molarity of the acid, at least not yet. 25.0 was the volume of the acid. We were given the molarity of the sodium hydroxide, that's the base, and we were given the volume of the titrant, the base, required to reach the equivalence point. You might wonder, do I have to put volume in liters? In this case, no. As long as those units are the same, they're going to cancel out either way. So we have just a simple mathematical or algebraic equation, 0.65 times 32.04 divided by 25, and you're going to get the same number we got before. So again, that's a great equation to use, but I caution you to only use that equation when you have a 1-to-1 mole ratio between your reactants. Otherwise, you might want to do the traditional volume times molarity and moles, and again, paying attention to the specific coefficients to convert from moles of one chemical to another. All right, here is another 1-to-1 mole ratio between an acid and a base. This is also a titration experiment, but instead of calculating the concentration of a chemical, this question asks you to calculate the molar mass of this substance. Benzoic acid is a monoprotic acid. A sample with a mass of 0.180 grams is dissolved into water and titrated with 0.125 molar potassium hydroxide. It requires 11.79 milliliters of the titrant to reach the equivalence point. So what is the molar mass of the benzoic acid? Well, now we have to convert from milliliters to liters, from liters to moles. There is a 1-to-1 mole ratio, but this time we're not going to do concentration. We're going to do molar mass. So molar mass is grams per mole. So I have moles of benzoic acid, which I'm not rounding off just yet because it's not my final answer. 0.180, that's my mass. Divide that by the number of moles I have, and our molar mass works out to be about 122 grams per mole. So you can use a titration experiment to do calculations for either an acid-base reaction or possibly an redox. In fact, I think you'll see that redox titration in your homework problem today. There are a variety of types of chemical reactions. One of them is acid-base. For more information about acid-base reactions, you can go back and watch the first video that we launched back a couple of weeks ago, and that would be topic 8.1, Introduction to Acids and Bases. In that video, I had mentioned that a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Also in that video, I had shown you an AP free response question in which we had an acid, propanoic acid, and it was reacting with water. So this chemical right here is called the conjugate base. I'll just say CB for short. And we'll call this the conjugate acid. Water was behaving as a base, so we'll say CB for conjugate base, and then the hydronium is the conjugate acid. So these were examples of conjugate acid-base pairs from that video 8.1 that I showed you earlier in this series. So let's go ahead and practice that a little bit. In the left, we have conjugate acid, and in the right, we have conjugate base. So how do you convert an acid to a base? You have to remove the H+. So take off H+ from HF and you get F-. F- is the conjugate base of HF. Take off one hydrogen from H2S and you get HS-. The hydrogen sulfide ion is the conjugate base of dihydrogen sulfide. Ammonium, the conjugate base would be ammonia. Notice that we go from +1 to 0 as far as the charge. And then the hydrogen carbonate or bicarbonate ion, its conjugate base would be carbonate. Notice I went from -1 to -2. So removing H+. How do I go from the conjugate base back to the conjugate acid? All you have to do is add H+ to the formula. So this is acetate, C2H3O2-. There is acetic acid, the conjugate acid. Notice I have no charge now on the formula because I was -1 and I added H+. HPO4, that's hydrogen phosphate. It has a 2- charge. If I add one more H, now it has a -1 charge. This is called methylamine. We've seen that before in other videos. This is the methylammonium ion. So I added the hydrogen to the nitrogen, and I changed the charge from 0 to +1. And then sulfate is a base. The conjugate acid would be hydrogen sulfate. So I added hydrogen and I changed the charge from -2 to -1. For more practice with acid-base reactions, I'm giving you the following. Each of the following reactions contains hydrochloric acid, HCl, as a reactant. However, only one of these reactions is classified as an acid-base reaction. So which of these three reactions is an acid-base reaction? Justify your answer. So feel free to pause the video, figure out which one you think is an acid-base, and then press play when you're ready to check your answer. So hydrogen is transferred from the HCl to the OH, that's a hydroxide ion, to produce water. So this is an acid-base reaction. And I will teach you in this lesson today that this first one is an example of redox or oxidation reduction. And this one here in the middle is an example of a precipitation reaction. And if I don't want to write out the word precipitation all the way, I might just write that as PPT for short. Okay, so that one in the bottom, the barium hydroxide plus the hydrochloric acid to produce barium chloride and water, that was an example of an acid-base reaction. A Bronsted-Lowry acid-base reaction always involves the transfer of H plus, or a proton, from the acid, the proton donor, to the base, the proton acceptor. Often, a Bronsted-Lowry acid-base reaction involves the formation of water, but not always. An acid-base reaction always involves the formation of an ionic compound or a salt. So here, for example, we have a base that does not contain OH-. This is ammonia. Here we have the acid. So when the proton is transferred from the acid to the base, we get the ammonium chloride as our product. And that would be a salt or an ionic compound. So sometimes we produce water in an acid-base reaction if we have H plus and OH-, but not always. If there's no OH-, then you're not going to make water. All right. Another example of practice. Feel free to pause the video when you're ready to check your answer. Which one of these three reactions that contains sulfuric acid, H2SO4, is actually an acid-base reaction? All right, if you've paused the video and hopefully had a chance to think about this before I reveal the answer, we can see a similar transfer of a proton from H plus to OH- to produce water. So this was an acid-base reaction. This was another example of redox. And this was an example of a precipitation reaction. All right, let's talk about redox. So oxidation reduction or redox involves the transfer of electrons from one substance to another. There is one species that loses electrons, and that is said to be oxidized. And then another species that gains electrons that is said to be reduced. So another way of thinking about this in terms of oxidation is there's something called the oxidation number. And the oxidation number will go up in value when it's being oxidized. And the oxidation number will go down in value that's being reduced. All right, here's an example of a redox reaction. This is a piece of magnesium, and magnesium is being burned in the presence of oxygen gas. And the product of this reaction is magnesium oxide. Here's your balanced chemical equation. So Mg plus O2 to make MgO. The magnesium is being oxidized from 0 to +2, and the oxygen is being reduced from 0 to -2. Another example of a redox reaction is the reaction between sodium metal and chlorine gas to produce sodium chloride. In this reaction, sodium is oxidized from 0 to +1, and chlorine is reduced from 0 to -1. Now, there is a helpful mnemonic device that you may have already learned in your chemistry class for the difference between oxidation and reduction as it has to do with losing or gaining electrons. So here is a picture of what you might recognize to be an oil rig. An oil rig is our mnemonic device. Oxidation is the loss of electrons. Reduction is the gain of electrons. Now, I'm talking about oxidation numbers. It is an important skill for you to be able to examine a chemical formula and assign the oxidation numbers to each element within that formula. So let's talk about some rules for assigning oxidation numbers. If you have an atom in its elemental form, the oxidation number is always 0. So hydrogen, lithium, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminum, etc. These are all 0 in their natural state. For a monoatomic ion, what you see is the oxidation number, that is the charge on the ion. So nitrogen in this case is -3, oxygen -2, fluorine -1. These are all monoatomic ions, +1, +2, +3, etc. Now, for a compound, Fluorine, being the most electronegative element on the whole periodic table, is always -1, no matter what it bonds with. You might wonder about this particular substance over here. These substances. Nitrogen actually carries an oxidation number of +3 in that compound because fluorine is -1. Oxygen would carry an oxidation number of +2 in oxygen difluoride, again, because fluorine is always -1. Now, for halogens such as chlorine, bromine, and iodine, they are usually, but not always, -1. If chlorine, bromine, or iodine are bonded to oxygen or fluorine, then they will have a positive oxidation number. So here, this is normal. This is HCl. H is +1, Cl is -1. This is also normal and typical. Sodium is +1, bromine is -1. Another example of a normal, typical, magnesium +2, iodine -1. But these are a little strange. So chlorine here would actually be +1. Bromine here is going to be +5. And iodine here is going to actually be +7. I'm going to give you some practice with how you can figure out the oxidation number within a compound, because I did that really fast and didn't break it down for you. So if you're confused about why is chlorine +1 or bromine +5 or iodine +7 in these compounds, let me give you some practice a little bit where I can slow that process down. All right, here we have more examples of some rules, and then I'll give you some practice. Hydrogen is normally +1, except when it's bonded to a metal. So in this situation, the alkali metal sodium is going to be +1, and that makes the hydrogen -1 when it's bonded to a metal. The alkaline earth metal calcium is +2, and that makes the hydrogen -1 when it's bonded to a metal. So in general, in terms of rules, hydrogen is usually +1. In general, oxygen is usually -2, except for that weird example I showed you earlier where oxygen was +2 because it was bonded to fluorine. Here's another weird example, and that is right here. So if hydrogen is +1, that means that this half of the formula would be +2. That makes this half of the formula -2. So if you have what's called a peroxide compound, H2O2 is hydrogen peroxide, then oxygen would actually be worth -1 in that particular compound. All right, let me go ahead and break it down for you. I've got KMNO4. Now, potassium is obvious and oxygen is obvious, but manganese is we don't know. So potassium is +1, alkali metal. Oxygen is normally -2. Manganese is we don't know. Well, how many oxygens do we have? We have 4 of them. That's -8. That's going to make the manganese in this particular compound +7, since in a neutral compound, the sum of the oxidation numbers of all the atoms are equal to 0. All right, another example. Sodium is normal. Oxygen is normal, and chlorine's going to be a little different, okay? You can't have chlorine being -1 in this particular example because it is bonded to oxygen. So sodium is an alkali metal, +1. Oxygen is normally -2, nothing strange about that. So what is our chlorine's oxidation number? Well, if you do the math, to get a total charge of 0, that's going to make the oxidation number of chlorine within this formula +1. So what happens if you have not a neutral compound? What if you have a polyatomic ion? Well, if you have a polyatomic ion, then the sum of the oxidation numbers is not going to equal 0, but rather the overall charge on the ion. So here I have bromine, which I'm not sure what its oxidation number is yet. I think it's positive something, but I'm not sure. And I've got 3 oxygens, that's -6. Now, if you think the bromine is going to be +6, remember that the overall charge of this ion, the bromate ion, is -1. That's going to make bromine +5 in this case to make the overall charge equal to -1. Here we have another example, the dichromate ion. We've got oxygen, which we know is typically -2. Here we have chromium, which we don't know. There are 7 oxygens, so 7 times -2 is -14. the two chromiums together are not going to be positive 14, but rather positive 12. That means that the overall charge of each chromium, or the overall oxidation state of each chromium, is going to be plus 6. All right, continuing with redox. A student made the claim that the reaction shown below is a redox reaction. Do you agree with the student's claim? Justify your answer in terms of the oxidation numbers. So let's break it down one at a time. Okay, now iron can sometimes be +2 or +3, but sulfur as a monoatomic ion is typically, sulfide is -2. That forces the iron to be +2 in that particular formula. Hydrogen is normally +1, so we'll go ahead and say +1. Oxygen is normally -2, and we have 3 of them, so that's -6. That makes the nitrogen +5. Now, on the other side of the equation, we still have that same NO3 ion. Nitrogen will still be +5 in the nitrate ion. So nitrogen is not changing. The iron is bonded to 2 nitrates that are each worth -1. That means that the iron has to balance the 2 nitrates. So iron is not changing either. And for hydrogen and sulfur, it's looking like each hydrogen is worth +1, and each sulfur in this case is -2. So having done a quick little analysis of the oxidation numbers, I disagree with the student's claim. This is not a redox reaction because the oxidation number of each element remains constant in this reaction. Now, earlier in this presentation, I showed you 3 reactions, and we called this one acid-base, and we called this one a precipitation reaction, and this one is redox. So it's zinc that is changing, and it's hydrogen that is changing. It's kind of obvious that hydrogen is changing because it goes from a compound to an element, and it's kind of obvious that zinc is changing because it's going from an element to a compound. So zinc is being oxidized from 0 to +2, and hydrogen is being reduced from +1 to 0. If you recall earlier in this lesson, I showed you another set of 3 reactions. We called this one acid-base. We called this one a precipitation reaction. And now here we have another example of element to compound and compound to element. So another example of a redox equation. Here the hydrogen is being reduced from +1 to 0, and the aluminum is being oxidized from 0 to +3. Now, with respect to redox reactions, you can split them up into what are called half reactions. So here is an oxidation half reaction, and here is a reduction half reaction. Remember, oxidation is the loss of electrons, and reduction is the gain of electrons. But notice that when I balance this equation, to get the charge and the atoms balanced, I have a different number of electrons. So I have 2 electrons lost in the oxidation half reaction, and I have 4 electrons gained in the reduction half reaction. So if you're going to add 2 half reactions together to get an overall equation, the number of electrons lost should be equal to the number of electrons gained. So I'm going to have to multiply my oxidation half reaction by 2. So now it looks like this to get the electrons to cancel out. And if you add these 2 equations together, I get 2Mg plus O2 makes 2 formula units of magnesium oxide. All right, so more example with oxidation reduction. Here I have iron that is being reduced from +3 to +2. I have tin that's being oxidized from +2 to +4. Now, as a result, I'm going to have to multiply the top reaction by 2 to get the electrons to cancel out. And now when I add these equations together, the electrons cancel out. Notice that the total charge on the left side of the equation would be positive 8, and the total charge on the right side of the equation is also positive 8. So don't forget, when you're balancing equations, that you balance both in terms of atoms and charge. Now, this reaction also features oxidation and reduction, but these are a little more complicated. Here we have nitrogen going from +5 to +2. That's going to involve 3 electrons. Here we have arsenic going from +3 to +5. But since 2 arsenic atoms are being oxidized from +3 to +5, that means I need a total of 4 electrons. Now, if you're looking at this equation, we have to multiply to get the electrons to cancel out. The top reaction is multiplied by 4, and the bottom reaction is multiplied by 3. Then when I add these equations together, the electrons should cancel out. What do you think I'm going to do with the fact that I've got water on both sides of the equation and that I've got H+ ions on both sides of the equation? Well, all we do there is we simplify. So 15 minus 8 would be 7 waters on the left. I still have the 4 nitrate ions. 16 minus 12 would be 4 H+ ions on the left. I still have my 3 units of As2O3. And on the right, I have those chemicals there. The total charge on each side of the equation happens to be 0 because I have 4 -1 nitrate ions and 4 H+ ions. So total charge is 0 on both sides. That equation is fully balanced. All right, we talked about in the lesson yesterday about precipitation reactions in which you form an insoluble or slightly soluble compound. I've already said that the solubility rules include sodium, potassium, ammonium, and nitrate. These compounds are always soluble in water. So here are 4 examples of precipitation reactions. The common feature in a precipitation reaction is that there should be a solid product. And as I gave you lessons yesterday about net ionic equations, you could pause the video right now and write the net ionic equation for each one of these 4 reactions, where the compound that I circled is going to be the only chemical that is featured on the right side of the equation. So if you've paused the video to write the net ionic equations on your own, I'm now going to reveal the answers. So net ionic equations look like the following. And again, notice that these are balanced in terms of both atoms and charge. All right, final debrief and summary. We talked about stoichiometry, titration, acid-base, redox, and precipitation reactions. Here is your AP exam practice problem for homework. So I'll give you a chance to take a screenshot. There are several screenshots here, several slides. So this is the first one. Here is the next one. And what I have done is I've zoomed in on the next slide here because it's kind of hard to read those burets. So here is a zoom in of that. And your final screenshot is this one. Okay, well, again, this comes to the end of the virtual chemistry lesson for today. Remember, there is a link to helpful chemistry resources in the video description. This has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. Don't forget to go to cb.org/tech for any needs of mobile tools or connectivity. Thanks for watching.